The core paradox of paleobiology is that behavior does not fossilize. Soft tissues like skin, muscle, and the complex neural pathways that govern social interaction degrade almost immediately, leaving behind only the most durable structural framework. This physical reality creates a significant limitation. Paleoanthropologists cannot directly witness the social hierarchies or the specific mating strategies of our extinct ancestors in the field. For decades, the standard narrative assumed a straight line of social progress. The theory suggested we evolved from violently competitive early apes and moved in a predictable trajectory toward the highly cooperative structures of modern humans. Testing that narrative requires a different approach. Researchers must read behavioral data through anatomical proxies, physical signatures in the bone that correlate with the living dynamics of the species. The first proxy is canine dimorphism. In primatology, the size difference between male and female canine teeth is a reliable indicator of intragroup aggression and the use of the jaw as a social weapon. The second is somatic sexual size dimorphism, or SSD. This measures overall body mass disparity between the sexes, serving as a signature of polygynous mating systems and acute environmental resource stress. Applying these metrics to two focal taxa, Ardipithecus and Australopithecus, reveals a dataset that challenges the linear model of human progress. The biometric ledger encoded in these fossils reveals a nonlinear evolutionary path. It shows a social trajectory responsive to the demands of a volatile landscape, diverging from the expected march toward cooperation. We begin this analysis 4.4 million years ago in the Ethiopian Rift, looking at the earliest well-documented hominin baseline, Ardipithecus ramidus. In modern great apes, the male jaw features a honing complex. This is a biological specialized structure where the upper canine is continuously sharpened against the lower teeth. These projecting teeth serve almost exclusively as social weapons. Males utilize them for displays of dominance and lethal intragroup combat to secure mating rights. The dentition of Ardipithecus ramidus stands in sharp contrast to that ape baseline. The fossilized jaw shows no evidence of those projecting dagger-like social weapons. The data shows an upper canine size ratio of just 1.06. Modern chimpanzees exhibit high disparity, while Ardipithecus approaches the near parity of modern humans. The lower canine ratio sits at 1.13, establishing this reduction in sexual disparity as a stable feature of the species. Paleoanthropologists refer to this reduction in weaponized dentition as canine feminization. Morphologically, this suggests a drastic decline in lethal male-to-male physical aggression within the Ardipithecus lineage. Anthropologist Owen Lovejoy links this reduced aggression to the pair bonding hypothesis. This theory suggests that bipedalism and low canine dimorphism reflect a strategy where males competed by provisioning females with food rather than through physical dominance. If this model is correct, our earliest evolutionary step was a shift away from physical dominance and toward complex social cooperation. If pair bonding and cooperation were successful adaptations 4.4 million years ago, we would expect those traits to strengthen and become more pronounced in later species. To test this, we look at Australopithecus afarensis, which occupied East Africa about 1 million years after Ardipithecus. The primary difficulty in analyzing this species is the fragmentary nature of the fossil record. Looking at the Lucy skeleton, the extent of missing skeletal mass makes it difficult to estimate the size of the living animal. Without intact, complete skeletons, researchers cannot directly weigh and compare male and female mass. They have to work around the missing evidence. The workaround is the geometric mean method, a statistical tool used to estimate the size of fragmentary individuals. This aggregates measurements from isolated postcranial elements, like a lone femur, and calculates a normalized body mass estimate. But a critical flaw remains. Without an intact pelvis, the biological sex of the individual bone is uncertain. To solve for this uncertainty, paleobiologists use a technique called iterative resampling. This simulation pulls from skeletal databases of modern primates, mimicking the missing data structure of the fossils. By running thousands of comparisons against known modern analogs, researchers build a robust statistical baseline accounting for the uncertainty of sex assignment. The results of this analysis reveal that Australopithecus possessed dramatically high somatic sexual size dimorphism. The males were significantly larger than the females. In primatology, this high size disparity is the morphological signature of polygynous mating systems, where large males compete intensely for reproductive access. This disparity also correlates with severe resource stress. In environments where food is scarce, smaller females can meet their metabolic needs and store energy for reproduction more efficiently than larger ones. These metrics suggest a major behavioral reversal. Instead of progressing toward cooperation, the Australopithecus lineage moved back toward intense hierarchical competition. We can visualize this evolutionary zigzag by plotting the data on a dual-axis scatterplot. We will map canine dimorphism as a proxy for aggression against body size dimorphism as a proxy for mating competition and stress. Ardipithecus ramidus sits in the lower left quadrant, exhibiting low aggression and low body size disparity. This represents the early cooperative baseline. Australopithecus afarensis plots in the upper left. While it retains low canine aggression, its body size disparity is high, indicating a return to competitive, polygynous social structures. This nonlinear map shows that hominin social behavior did not follow a fixed trajectory. It adjusted according to the needs of the moment. What exactly caused this radical social reversal in Australopithecus? The driver was tectonic and climatic volatility of the East African Rift Zone during the Pleistocene. During the Early Pliocene, Ardipithecus lived in stable, closed woodlands. These habitats offered reliable food and immediate arboreal safety, supporting a pair-bonded strategy. But the climate cooled rapidly, shrinking the forests and expanding the resource-scarce, open grassy savannas we see here. This open landscape exposed hominins to hyper-specialized apex predators. In this environment, selective pressures favored larger, highly competitive male bodies suited for group defense and the hoarding of limited resources. The history of our lineage is a record of pragmatic biological responses to a changing world, encoded directly into the